Dear students, welcome to the problem solving session on Milne Thomson's method part 3. In the first video, we learned the working procedure and then we solved few problems on video number 2. In this session, we are going to solve a different problem. Before going into the problem, let us have a quick recap. The working procedure for real part or imaginary part is given. We have to identify whether the given problem is real part or imaginary part. Step 2, we have to find the corresponding partial derivatives. Step 3, by Milne Thomson's method, we use the formula. Step 4, we have to integrate f dash of z on both sides to find the analytic function f of z. In today's session, we are going to see a different problem. U is equal to sine 2x. In the denominator, we have cos h2y plus cos 2x. We know that cos, sin, tan, secant, cosecant, etc. These are all trigonometric function. Let us explore some basics where this cos h, sin h originates. Recall the Euler's formula. E power I theta is equal to cos theta plus I sin theta. If you write e power ix, we get cos x plus I sin x. Then e power minus ix is cos x minus I sin x. When you add these two equations, we get 2 cos x is equal to e power ix plus e power minus ix. Similarly, when we subtract these two equations, we get 2i sin x is equal to e power ix minus e power minus ix. From this we get cos x is e power ix plus e power minus ix by 2. Similarly, sin x is e power ix minus e power minus ix by 2i. We can see the typed version. So we know that cos x formula is e power ix plus e power minus ix by 2. If I am replacing x by ix, we get e power I of ix plus e power minus I into ix divided by 2. That is e power minus x plus e power plus x, because I into I is I square is minus 1. We get minus x here. Here minus I square is plus x. Therefore, cos ix is e power x plus e power minus x by 2. So we say this as cos hx. So cos ix is cos hx. Similarly, if we replace for sin, we get sin ix is equal to e power I into ix minus I into ix divided by 2i. So we get e power minus x minus e power x divided by 2i. Now I will take this minus outside. So we get e power x minus e power minus x by 2i. We never keep the complex number in denominator. So I'll multiply and divide by I. Simplifying, we get minus I into e power x e power minus x divided by 2i square. I square is minus 1. So minus minus get cancelled. We get I into e power x minus e power minus x divided by 2. So this is equal to I into sin hx. Therefore, cos of ix is cos hx. Sin of ix is I into sin hx. Cos hx formula is e power x plus e power minus x by 2, and sin hx formula is e power x minus e power minus x by 2. Hope you understand. Now we can compare the formula for cos and cos hx. Similarly, sin and sin hx. And we know the famous result, cos square theta plus sin square theta equal to 1. But in the case of hyperbolic functions, we have cos h square x minus sin h square x equal to 1. If you want, you can pause and see the proof. Whenever I put x equal to 0, cos h0 is e power 0 plus e power 0 by 2, that is 1. Sin h0 is e power 0 minus e power minus 0, that is 1 minus 1. It will become 0. So sin h0 is 0, cos h0 is 1. Similarly, now we had a doubt. We know differentiation of sin x is cos x and differentiation of cos x is minus sin x. But what happened for this hyperbolic function? Differentiation of sin hx, we know sin hx is equal to e power x minus e power minus x by 2. If we differentiate this, we get e power x. Then e power minus x differentiation is minus e power minus x, minus into minus, plus divided by 2. So differentiation of sin hx is cos hx. Similarly, differentiation of cos hx is the differentiation of e power x is e power x, and e power minus x differentiation is minus e power minus x. This is nothing but sin hx. So in hyperbolic function, we don't get negative. Differentiation of sin hx is cos hx. Differentiation of cos hx is sin hx. So there is no minus sign. I think this is more than enough for our problem solving purpose because we have cos hy. Now let us go into the problem. Given u is equal to sin 2x divided by cos h2y plus cos 2x. We have to find the corresponding analytic function f of z. As usual, step 1 we identify the given problem is real part u. Now we have to find the partial derivatives, that is ux and uy. We have to recall the formula. Differentiation of u by v is equal to denominator v square, numerator v du minus u dv, quotient rule. Okay, now let us consider this as v and this as u. Then differentiation of u partially with respect to x, denominator we get cos h2y plus cos 2x whole square, that is v square. In numerator v du, let us keep cos h2y plus cos 2x as it is, and differentiation of sin 2x partially with respect to x is 2 into cos 2x minus, if I keep sin 2x as it is and differentiating cos h2y plus cos 2x. Since we are differentiating partially with respect to x, the first term will become 0. Second term cos 2x differentiation is minus 2 into sin 2x. Now simplifying the numerator further, we have 2 cos h2y cos 2x plus 2 times cos square 2x minus into minus plus 2 times sin square 2x. So we know the formula. Cos square theta plus sin square theta is going to be 1. So now take 2 in common. Cos square theta plus sin square theta is going to be 1. So 2 into 1 is 2. And here we have the remaining 2 cos h2y and cos 2x. Even we can take this 2 out, and then we can keep 2 times cos h2y cos 2x plus 1. Denominator remains the same. So we found ux. So in this problem I can't do the table because this is little big. So I'm finding one by one. Next we have to find partial derivative of u with respect to y. So denominator as usual v square cos h2y cos 2x whole square. In the numerator v du minus u dv. When I differentiate sin 2x, it does not have any y term. So cos h2y plus cos 2x, differentiation of sin 2x with respect to y is 0 minus, if we keep sin 2x, differentiation of cos h2y is 2 times sin h2y. Just now we saw differentiation of sin hx is cos hx and differentiation of cos hx is sin hx. We don't get negative. Second term will become 0 because it does not have y. Now 0 into anything is 0. Simplifying this, we can write this as minus 2 times 2 into sin 2x sin h 2y. Now for your convenience, I am putting the table. I am writing the u, ux and uy. Now we have to replace x by z, y by 0. Just now we see cos h0 is 1. Now we replace x by z and y by 0. In the denominator, we get 1 plus cos 2z whole square. In the numerator, cos h0 is 1 and cos 2x will become cos 2z plus 1. So now I can cancel this numerator with denominator. Finally we get 2 divided by 1 plus cos 2z. When you come for uy of z comma 0, if you put sin h0, it is 0. Since we see cos h0 is 1 and sin h0 is 0, so uy of z comma 0 is 0. Now we have to simplify this further. We know that cos 2 theta is equal to 2 cos square theta minus 1. So 1 plus cos 2 theta is 2 cos square theta. So I can simplify this further as 2 divided by 2 cos square z, because 1 plus cos 2 theta is 2 cos square theta. 1 plus cos 2 z is 2 cos square z. I can cancel this 2. 1 by cos square z is secant square z. You can see the typed version. Therefore ux of z comma 0 is secant square. Uy of z comma 0 is 0. Now the real part is given. We have to recollect f dash of z is ux of x comma y minus I into uy of x comma y. By Milne Thomson's method, this is equal to ux of z comma 0 minus I into uy of z comma 0. Both datas are ready. Therefore, my f dash of z is secant square z because uy of z comma 0 is 0. Now we have to integrate this. We know that integral f dash of z dz is equal to integral secant square z dz. Integration of f dash of z is f of z. Tan x differentiation is secant square x. Secant square z integration is tan z plus c. This is my required analytic function. Hope you understand, students.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.